In this video, we are going to create a NodeBuilder utility class. Up till now, we have the ability to create node networks using our interactive editor. Now, as we progress into the pathfinding algorithm code, we would like to be able to have a very reliable test scenario. We'd like to have a system of nodes that will let us clearly test how the algorithm is working rather than dealing with obscurities with different versions of a node network. Also, it would be nice to test larger node networks without having to spend a lot of time rebuilding the network over and over again as we test the algorithm. So what we're going to do is we're going to put together two utility methods that will let us create a set of nodes. The first method will let us create a grid of nodes, and the second will let us create a circle of nodes. The other thing this will do for us is, since we're going to be creating these procedurally, we will have exactly the same result with each call to these methods, and that makes a very reliable test scene to use when testing the pathfinding algorithm. So to get this started, let's move up to the editor folder in our project and add a class. This class is going to be called NodeBuilder. Inside of the NodeBuilder class, we'll begin with the subnamespace. We'll remove the .editor subnamespace, and we will need access to some of the types in the XNA namespace, so we will add a using statement for Microsoft.xna.framework. Now, the NodeBuilder class itself is going to be static, and we will have two methods inside of NodeBuilder. The first method is going to be used for building grids of interconnected nodes. Let's define this method as public. It will, of course, need to be static, and it will have a void return type. The method name is going to be buildGrid, and there are a handful of parameters we need to take in order to describe a grid. The first is going to be a position. We'll take in a vector2 called position. Actually, let me grab some spelling on that. And not doing so well with spelling. There we go. Vector2 for holding position, again, because we'd like to be able to place the grid somewhere on the screen. The next parameter we'll take is actually two parameters. We want to be able to tell how many sections, or rather how many columns and rows we would like in the grid. So we'll take in two integers. The first will be called numx, to indicate how many elements we would like across the grid horizontally. And we'll take in a second integer called numy, so we can tell how many rows we have in the vertical direction. One final parameter we'll take in will allow us to describe how far apart the individual grid points are spaced. We'll call this spacing. Alright, that takes care of our method signature for buildGrid. Now we're ready to jump in and begin creating nodes. So a brief description of how this is going to work. We're going to create a temporary list to hold all of the nodes that we create. The reason we'll do this is we're going to be creating the nodes and need to connect those nodes to earlier nodes that were created. So we need to remember other nodes. For example, if we connect the node to the last node horizontally, we'll need to know what the node right before the current node is. If we want to connect the node to a node on the row above, then we'll need to know a node that is numx away from that node. So we need to remember nodes after we create them. So we'll create a list here inside of the buildGrid method, a list of type node, which we will call nodes. We'll turn around and initialize this to a new list of type node. Alright, the next thing we need to know is how many nodes we will be creating, and we can derive that number by simply multiplying the number in x by the number in y. So let's make an integer variable called count and set that to be equal to numx times numy. Alright, now that we know how many nodes we will be creating, we can begin a for loop to loop over all the nodes that should be created. We'll say for index variable I begins at 0, continues looping as long as it is less than the count variable. Now inside of this loop, we're doing something interesting. We're looping through all of the possible nodes, but we don't yet know where the nodes should exist in two-dimensional coordinates. since we're creating a grid, we need to space these new nodes in X and Y on the screen. So what we'll do is we will actually derive an X and Y position inside the grid based on where we are in the number of nodes created and how wide the grid is by looking at num_x. So what we'll do is we'll create some local variables inside of the for loop. The first will be an integer called x. X will be equal to the current count, the current index represented as I, modulus the number of nodes we have in the grid in X. And the idea here is that this is simply going to cause X, you could say, to advance and then restart every time we move down to a new row. Another thing to note is that we're looking at these in terms of, you could say, a theoretical grid, meaning these grid points are exactly 1 unit apart at this point. We'll handle actual on-screen spacing later as we build the nodes. Now the other piece of information we need is where in Y do these nodes exist. So we'll make an integer variable Y that is equal to I divided by num_x. The idea here is that we will leverage the fact that we're going to get truncation and any remainder since we're doing integer division. We have the integer I and the integer num_x. So as we divide I against num_x, as long as we're on the first row, I divided by num_x doesn't get high enough to go above 1. Or, matter of fact, it stays below 1, and each time gets truncated to 0. It's only after we move down to the second row does I get large enough to have a full integer portion survive the division and get stored in Y. Then we continue to increase as we go row by row. Alright, now that we have an idea of where these nodes exist in 2D space, it's time to begin creating nodes. Let's make a node local variable, set that to be a new instance of a node. Then we need to make sure that we remember that this node got created by adding it to our nodes list. So nodes.add, and then we'll pass in our new node. Now we need to set the position of the node. So we'll say node.position is equal to a new vector2, and we'll pass in x and y. Now at this point we need to take x and y, which are simply representing grid positions, and multiply them by spacing to get real actual pixel locations. So that means for the x component of our vector we need to multiply that by spacing, and multiply y by spacing to get the appropriate location. Now, once we create this vector2, we will offset it by the position that we're passing into build grid. So we'll say plus position, and that way we'll position the entire grid as a whole. Alright, now with this in place, let's actually put together a test scenario so we can begin running this code. We're at the point now where we need to handle the connections between nodes, but let's first see what these nodes are looking like on screen. Then we can watch the connections as they get created. So let's jump over to the scene editor, and let's jump up here to the constructor right after we set up our mouse input handlers. Let's put together a call to NodeBuilder and issue a call to buildGrid. For position, let's pass in a new vector2, giving values of 80 by 70. For the number in x, let's give the number of 9, and the number in y as 7. For spacing, let's give a spacing value of 80 pixels between each grid unit. Now let's build and run the game, and we now have a grid of nodes that have been created. Of course, none of the nodes are connected yet, but I just wanted to show what these are looking like in real actual screen space so we can see the connections. Let's also talk briefly about how we will go about connecting these nodes. We have 4 different connections that need to be made per node. Let's just start with this node as an example. The connections we need to make are 1, a connection from the node to the previous node. That will make 1 horizontal connection. Another connection we need to make is from the node to the node directly above it on the previous row. That's a second connection. That takes care of doing our vertical and horizontal connections. We would also like to add diagonal connections between each node. For the first diagonal, we'll take the current node and connect it to the node up and to the left. So on the previous row, one behind it. and also on the previous row, one ahead of it. Now the nice thing is that each of these connections are always looking back at nodes that already exist, so we can create the connections node by node as nodes get created. So let's get started here in NodeBuilder and begin putting some connections together. Again, the first connection is going from the current node to the previous node. Now let me bring the game back up and note one exception to this rule. We were talking about just saying the node that came before. We don't want to use the node that came before if we're already on the left, because if we do so, the node that came before is all the way up here on the previous row. As a matter of fact, we could easily show that if we do no checks and say node.bidirectional connect, passing in the previous node, which would be in the nodes list specified by the index variable I minus 1. And looking at this, we may not actually be able to execute this outright because we'll try to connect to the node that came before the first node, which doesn't exist. If we try to access node subelement -1, that's obviously an error. So I was hoping to be able to show it and show the crossing diagonal connections, but we won't be able to run without this. We will need to do a check and say if x is greater than 0. And if that's the case, then begin doing connections. Because, of course, x is going to reset to 0 every time we advance to a new row because of the modulus operation here looking at the index variable. Also to note where we're connecting to, I'm going to drop a comment down saying that with this connection we are connecting to the left. Now if we run, we can see we have horizontal connections between all of our nodes because we go from each node to its previous node. Unless we're at 0 and x, then we don't bother making the connection. Also, I just thought of a way of showing the diagonal connections, the accidental diagonal connections. Let's change this to if I is greater than 0. So the only time we don't connect is on the very first node. If we run this, we see the problem is that the node previous or prior to this node is, of course, the node over here, and that's the connection that gets created. So we can't always connect to the previous. We can only connect to the previous when x is 0. Alright, moving on, we can now address the connections in the up direction, connecting to the previous row. We need to do an if statement here as well because we can always connect to the previous row unless we're the first row. If we're the first row, then there has been no prior row to connect to. We'll do this check by looking at the y variable and making sure that it's greater than 0. So we have advanced past the first row. If that's the case, then we'll take the node and we'll issue a bidirectional connect to nodes. So now looking into the nodes list, we need to look back in the list by an amount of nodes equaling exactly one row. So starting from where we're at in this current node, we need to step backwards exactly one row's worth of nodes, which is represented by the number of nodes in x. So we can finish off the brace and the parenthesis, terminate the statement, and drop a comment noting that this will be creating a connection in the up direction. So looking at the code here, we have a syntax error with the way that we're referencing our nodes. So looking at nodes, we're looking at the node, rather I had the node listed instead of the nodes list. So correcting spelling has cleared that up. Let's run and test, and very nice. Now we have both vertical and horizontal connections between all of our nodes. We could even jump into our move mode and see that, yes, all of these do indeed connect properly. Now we also want to create diagonals between each of these nodes. So what we'll do is we'll jump in here and create an additional if statement. The first diagonal is going to be up and to the left. So we need to do a check and make sure first that we are past 0 and x, because we can't move to the left if we're already all the way on the left. So if x is greater than 0, and we're past the first row. We can't connect diagonally up if we're at the top. So if y is also greater than 0. If this is the case, then we can make a connection using node.bidirectional connect, looking at the nodes list, and looking at subelement I. We know that I minus num x is going to give us the previous row. Minus 1 is going to give us the previous one, but then 1 to the left. So that finishes up the node index. We can close this off with a parenthesis, terminate, and then note that this is the connection for the diagonal left up. And we can run and see that we now have diagonal connections in one direction. Now we need to get the diagonal connections in the forward direction. So moving down here, let's do one more if statement and say if x is, well, we're in an interesting scenario. In order to connect forward, let me point this out visually. It'll make it easier to explain. If we were at this node, we need to connect forward to this node. If we're at the very end, there's nothing to connect forward to. That means that x has to be less than the maximum in x. So it has to be less than num x in order for the connection to work. Also, y is going to have to be greater than 0 because we couldn't connect off of the top row on any of these. So the check is going to be if x is less than num x minus 1. The minus 1 just to account for the fact that x is going to be 0 based and num x is not. So if num x, or x is less than num x minus 1 and y is greater than 0, then we can proceed with the connection. We can say node.bidirectional connect, passing in nodes sub-element I minus num x. Again, that moves us exactly up one row, but this time plus 1 to move to the node to the right of us. Now we'll close off the bracket and the parenthesis, and note that this connection is in the right dash up direction. Now if we run, we can see we have connections created in the diagonals as well. Now the interesting thing about this scenario is this allows us to test the pathfinding algorithm in a more tile-based manner, because of course these kinds of pathfinding algorithms can work both in free-form node networks as we've created here, and in tile-based setups where any given tile has exactly 8 tiles surrounding it. If we look at the way this node is connecting, we have exactly 8 connections from this node, up, down, left, right, and 4 diagonals. So if we would like to test how the algorithm would work in a tile-based scenario, we can simply build a standard grid and simply leave all the nodes placed equally spaced from each other. So that's one of the added benefits of having this procedural generator method, is we can also test tile-based operation using our freeform node network. Alright, that nicely takes care of building grids, so let's take a look at building circles. Let's see, we're here currently in the NodeBuilder class, so let's move down right after the build grid method, and let's make a new method. Let's make a public static void method. We'll call this method build circle. And into build circle, we need to take in some parameters to describe the circle. First is going to be a vector2 to describe where we would like the circle. We'll call this position. Next, we'll take in a radius for the circle, and we'll take this parameter in as a float. So we'll have a float radius. And finally, we'll take in a count to say how many nodes we would like to use in the creation of this circle. So with our method signature in place, we'll brace in the method and begin working. Once again, we're going to create a temporary list of nodes so we can look at past nodes that have been created in order to establish connections. So we'll make a list of node called nodes and set that to be equal to a new node list. Now, since we already know how many nodes we're going to be creating, we can begin our for loop. We'll say for index variable I continues until we are one less than the count. Or, continues as long as we are less than the count. Now, inside of this loop, we need to begin creating nodes. So once again, we will make a node variable and use that to hold a reference to a new node. Once we create the node, we will add it to the nodes list. So nodes.add node. Now we're ready to position the node, but we need to do a few calculations in order to derive the exact position. since we're positioning these around a circle, we'll actually need to take some rotational math into account. Since we'll just imagine that as we progress node by node, we'll just consider that progressing a certain percentage around a circle. Since if we divide I against count, we can find the percentage in a 0 to 1 range. If we multiply that by 2 pi, we'll have the percentage in terms of a whole circle in radians. And if we use that value in radians, we can convert that back to a vector using sine and cosine. So let's put this together. First, we need to figure out where our rotation around a circle is. So let's make a float, and let's call it rotation. So float rotation is going to be equal to I. Now when we do this division, we're needing to begin with a value in a range of 0 to 1 as a decimal value. And both I and count that we're going to be dividing against are integers, so let's first cast I to a float to make sure that we do the actual division operation using floating point types. So we'll say float I divided by count. Now we need to multiply this, but I want to make sure that we handle the correct order of precedence, so I'm going to put this portion of the expression in parentheses. So the idea is that the result here is a percentage of how far we are into the circle in a 0 to 1 range. Now if we take that range and multiply it against math helper dot 2 pi, that will give us a value in terms of radians going around a full circle. Alright, now that we have the rotational value, we need to resolve that to an actual x and y position that we can plot on screen. So let's calculate that, but then immediately turn around and store it into the node's own position. So it's time to take node.position and set it to a new vector 2. Now in this vector 2, we need to resolve the rotation using cosine and sine. In order to grab the x component of the vector, we'll use math.cosine on the rotational value. So if we say math.cosine, we can pass in rotation. Now the math cosine function is going to return a double. We need floats to store in the vector 2, so we'll cast this to float. Now that will take care of the x position. Now we need to take a look at y. We'll do exactly the same thing, only using sine of the rotation. So we need the float casted result of math.sine for the variable rotation. So with that value representing the x component, we're now ready to finish the parenthesis for the creation of the vector 2 and terminate the statement that is assigning this to our node's position. Now let's jump down, and at this point we're ready to, well, almost ready to take a look at connections. We've got a circle, but since we're assigning the positions directly from sine and cosine, we'll end up with a circle with a radius of, I believe, 2, because we've got 1 to negative 1. So really overall, no, actually I take that back, that's a radius of 1. Since we'll go 1 positive, 1 negative, if we sample that radius, that would be exactly 1. We've passed in a radius that we would like to use, so it's actually beneficial, the fact that this vector that's being generated has a value of 1. We can directly multiply that against radius, and that will give us the true radius that we requested. So that means once we assemble the vector 2, we can multiply it against radius, and I just noticed something about the radius variable. It appears to be misspelled, so let's hit F2 to bring up refactoring and correct this to radius. Very nice. Now we have the radius taken into account for our circle. While we're at it, there's one last thing to put into place, and that is the position of the circle. Because at the moment we'll have the correct radius, but the circle will be centered around the origin at 0, 0. We can correct this by simply putting our position parameter into play by offsetting the position as plus position. Alright, that should now take care of creating the circle itself. We still have to deal with connections, but before we jump into connections, let's show the circle in use. Let's jump back over to the scene editor, and let's temporarily comment out our grid. Let's jump down and look into the NodeBuilder and invoke the build circle method. For position, let's give a new vector 2 of, let's say, the center of the screen, which would currently be 400 by 300. For a radius, let's give a radius of 200 and give 8 nodes as the number of nodes we would like to appear in the circle. So now if we run, we see we have a series of 8 nodes all created and positioned in a circle. So that portion of the code is working nicely. Now we can address all of the connections. Before we make connections, we want to do a check and make sure that we are past the first node. The logic we'll use here is we'll simply walk node by node, connecting ourselves to the previous node. So we'll say if I is greater than 0, then we'll take the current node, and we will run a bidirectional connect on the previous node. To get the previous node, we'll look into the nodes list and access sub-element I minus 1. Then we'll close up the parentheses for the connect operation, terminate the statement, and we're ready to test. So now we do have connections, except that we're missing one. And that makes sense, because if we're watching the logic, we don't make a connection from the first node. We move on to the second node, make a connection back, third node, make a connection back, so on and so forth until we hit the last node. The last node, we make a connection back, and that's the last connection we make. What we need to do is, after the creation of the circle, we need to go back to our first node and establish this last connection. So we'll do this outside of the loop. So once we have finished the loop, where we create the nodes and create all but one of the connections, we'll make a final connection that goes from nodes sub-0, which is the first node. So we will run a bidirectional connect against the last node. To get that, we'll look at nodes, sub-element of nodes dot count minus 1. Close off the bracket and close off the parenthesis for the connect call. Now we can run, and we have all of the connections in place all the way across the circle. So now we have a way of making arbitrary circles positioned wherever we would like and with any number of nodes. So again, this just adds a tool that we can use to quickly create more complex scenes in order to test our pathfinding code. Now there's one last thing I want to do to get the scene ready for use before we move in to the pathfinding algorithm itself. Back inside of our scene editor, what I'd like to do is build a special scenario with a grid. So I'll comment out the circle. As a matter of fact, I'll remove the circle entirely because we're going to be using the grid for the majority of the testing while building the algorithm. Once again, this grid is going to create a series of nodes, but to make a more complex scene, what I'd like to do is delete some of these nodes from the middle. Matter of fact, just imagine that as we're building, we had done this operation, where we delete these nodes here in the center. What's nice about this is this gives us the concept of an obstacle, where if we were at this node and wanted to navigate to this node, we couldn't use a straight line. We would be forced to navigate around the obstacle. This gives us the ability to test, A, how our algorithm is working, and B, the efficiency. Do we slam into the obstacle before avoiding it, or do we pick a more appropriate path? But again, this is a scenario that we will test frequently when building the algorithm, so it would be nice to be able to build this without having to delete these nodes out by hand. Now, what we'll do is we'll put together some code that will rely here on this grid. What we'll do is we'll simply address some nodes by number and delete them out. We'll actually have to delete them backwards, in essence, since we're going to use the actor list in order to perform the deletion. If we begin counting nodes, we could say that this node is node 0. And because we're closely watching how actors get created, we know that that is also actor 0. So if we're counting across, we can say that that's 0, 1, 2, 3, and 4. That gets us to the center. Now, if we add the total number of nodes that we're using in a row, which is currently 9 nodes, if we add 9 to this number, we'll drop down. If we add 9 again, we'll get to the first node that we want to delete. So that means we'll need 7 plus 9 plus 9. Another thing to keep in mind as we do the deletions, that actually takes elements out of the actors list, and that means we're shortening the list. So to keep everything in line as a column, we'll actually have to start here at the bottom and delete upwards. So if we take that specific node element and delete it, actually we want to cast these two nodes to make sure that all the proper connection cleanup occurs. So what we'll do is we'll take actor.actors. We'll begin at sub-element 40. As a matter of fact, let me show sub-element 0, just to keep the counting making sense with what we've seen on screen. We want to cast this as a node. Then we want to take the entire operation, put this into parentheses, so that we're actually looking at the node itself, and then we'll call delete. Again, the reason we're casting to node is to make sure that the node-specific connections get cleaned up. Now if we run, we can see that this takes out node 0. If we advance this to element 4, now we take out one in the middle. If we advance by 9, which should be 13, we drop down a row. And we can continue advancing by 9 to get lower and lower here in the grid. If we advance all the way to 40, we delete the bottom of the 3 that we were attempting to delete. If we walk backwards, we don't have to worry about the later deletions later in the list affecting positions earlier in the list, so we'll make sure that this deletion happens first. Now for the second deletion, we'll delete out node 31, so you could say we subtract 9, access node 31, and delete it out. That takes care of the second one. Subtract 9 again. Whoops, not cutting. Let's bring that back. Copy and paste to duplicate. And finally access node element 22. Delete it out, and now we have removed all of those nodes automatically on scene creation, so we can use this as a reference scene when building our algorithm. And now I will point out that this is very fragile code as it's been presented, since it's depending on multiple things. It's relying on these actors actually being nodes, and it's relying on these exact node numbers. So again, you wouldn't want to use this in a full scene in a game, but in this case we're not building a game, we're writing an algorithm, and this makes a perfect testbed for us as the algorithm designers. So just pointing out that this is very inelegant and fragile code, but it works nicely to allow us to quickly build a reference scene. So with all of this in place, we have created a NodeBuilder utility, and we have the ability to build grids, circles, and our special grid for testing. So with this in place, that is going to wrap up this video.